Hi everyone, in this video we're going to keep talking about real zeros of polynomial functions, and this time we're going to be finding the real zeros of the functions. So in the previous videos we used the rational zeros theorem to list our possible rational zeros. We learned about Descartes' rule of signs, telling us about the number of positive and negative real zeros, and we learned about the remainder and factor theorems. And so we're going to put all of that together to actually find real zeros of polynomial functions and also solve those functions if we set them into equations. Okay, so our example here, we're going to find the real zeros of this function, and at the end we're going to write it in factored form. Okay, so we have a third degree polynomial, and we're going to use that to determine that there's a maximum of 3 real zeros. So we want to find these real zeros, and we want to use them to help us factor this function. Okay, so we have at most 3. So next, let's use Descartes' rule of signs to determine how many positive and negative real zeros we have. So our function, let's write down the original, was 3x cubed plus 4x squared minus 5x minus 2. So if we count the sign changes, this is positive to positive, so no change there. Positive to negative, so 1 change. And then negative to negative, so no change there. So there was 1 sign change for positive f of x, and so there's 1 possible positive real zero, so 1 positive real zero. Then when we plug in a negative x and simplify, notice that it goes from negative to positive, so that's 1 sign change. Positive to positive, so no sign change there. And positive to negative, so a second sign change. So there's 2 or none, because remember how that goes from Descartes' rule of signs, you start subtracting 2. So we have 2 sign changes here, so there's 2 or subtract 2, 0. Negative real zeros. Okay, so that's going to help us narrow down our results. So one positive real zero and 2 negative or possibly no negative real zeros. So now we're ready to use our rational zeros theorem to identify a list of possible rational zeros. Then once we have that list, we can use a few different things. We can use substitution, synthetic division, or long polynomial division, like long division, to determine each of those rational zeros if it is in fact a zero, meaning when we plug it into our function, we plug in the real zero, what we're calling a real zero, into our function, the answer is 0. And then we'll factor afterwards. So we have options here, and we'll just do different ones for the examples. And then you keep doing this until you've found all of your zeros, or you can factor the rest without using the list. Okay, so listing our possible rational zeros. Remember how this goes from the previous video. You take the factors of the constant, so the factors of -2, and you divide them by the factors of the leading coefficient, so the factors of 3. And so -2, what goes into that is 1 times 2, or -1 times 2, so plus and minus 1 and plus and minus 2. And the factors of 3 are just plus and minus 1 and plus and minus 3. So when you divide these, notice what you get. You get 1 divided by 1, which is 1. Let me change colors. 1 divided by 3, which is 1/3. And then 2 divided by 1, which is 2. And then the last one is 2 divided by 3, which is 2/3. And so if you want, you can write this list out all the way. I'm just going to write it expanded as -2, -1. I'm going in order from small to big. -2/3, -1/3, positive 1/3, 2/3, 1 and 2. So this list of possible rational zeros has 8 numbers on it. We know a few things. We know that our possible zeros, our maximum number of zeros, is 3 from the degree of our polynomial. So we'll have at most 3 from this list. We also know that there's positive. We have 1 positive. So 1 positive and 2 or 0 negative. So from this list, only one of these positive numbers can work. And then on the negative ones, either 2 of them work or none of them work. Okay, so what you do is you test a number. So you have this list of 8 possible numbers. Pick any number you want and you test it. So what we're going to do is we're going to pick the number 1 from this list. This is just a choice. So you choose any number you want from the list. So we are going to choose 1, and we're going to use the method of synthetic division. And we're going to try to figure out if this is going to be a real zero. Okay, so the way synthetic division goes, we did this in a previous video, but you write this number here. This is going to be from our factor, possibly at the end, and you put that on the outside and you bring down this first number. Okay, these numbers here come from the coefficients. So notice this is 3x cubed, 4x squared, negative 5x, and negative 2. So those numbers come from your polynomial. Let me clean this up a little bit. And so synthetic division, you're just going to bring down the first number, and then you multiply 1 times 3 and put it here. And then you add. So that's where 7 came from. And then you do the same thing with the next one. 1 times 7, write it here, and then you add. That's where 2 comes from. And then you do that again. 1 times 2, put it here, and then you add, and that's where 0 comes from. And that's good news, because that means that the remainder, this is the remainder. This means that the remainder is 0, which implies that this was going to be one of our real zeros. Because when we plug it in, there's no remainder, so it is going to go right into a factor, and that is one of our real zeros. So if the remainder is 0, then that number is a real zero. So the number that we divided by, which we call C from our factors, so C is a real zero. Yay, this is good news. Okay, and so that's from one of our theorems that we learned in a previous video. So if f of 1 is 0, then 1 is as a real zero of our polynomial, and x minus 1 is a factor. This was from our factor theorem. Okay, so far what we know, let's kind of sum up what just happened. We made a list of possible rational zeros. We chose a number from the list. We used synthetic division to figure out if this goes in evenly, which it did. It had a remainder of 0. Our other option would have been to just plug that number in. This would have been the substitution method. Plug that number right into your function in for all the x's here. And if the answer is 0, then you know 2 things. You know that that number, 1 in this case, is a 0, and that x minus that number is a factor. Okay, so that means that our function has a factor so far of x minus 1 and then some other things. Okay, and so the other part, once you find one of the factors, then the rest of it starts to get much simpler. So this part here, I want to show you where this came from. Let's go back to what we just did. That was actually, let's clean this up a little bit, that was from the third row of our synthetic division. So if you did long division, you would get the same thing, but if you use synthetic division, this is what's left over when you divide. So this used to be x cubed, this was x squared, and so on. And so when we divide, this is technically by x minus 1. Then what's left over is 3x squared, because we divided by x, plus 7x plus 2. And if that doesn't make sense to you, this is another quick way to remember this. If this is a third degree, if this was third power on x, Then when you divide using the synthetic division, just subtract 1. This is going to be 1 degree less, 1 power less. So this is x squared. And so that is where we got this from, this factor right here. And at this point, it's a quadratic polynomial at this point. So you don't have to continue doing the list that you had if you don't want to, because we have other techniques. We can factor this one using other techniques we know. All right, let me go back to our list again really quick and show you something else that came up, just to kind of put this all together for you. We have that 1 was one of our real zeros, and that's a positive number. And so from Descartes' rule of signs, we have 1 positive real zero, meaning if we want to go back to our list, we can now exclude some things. We can say none of these other numbers on the list that are positive are going to work. So we don't even have to bother and take the time out to figure out if those numbers would be the real zeros, because they're not going to be because of Descartes' rule of signs. So any other real zeros would be from the negative side of the list. Okay, so now let's continue. And we have what's called a depressed equation of our function, which is this leftover part that we got after we found one of the factors. And so we're going to just work on that one. We want to find the zeros of just this depressed equation part, or the remaining factor. And it is a quadratic equation, so we don't have to necessarily use our list. We can if we want, but let's go ahead and just use our factoring techniques from the past. And this one factors as 3x plus 1 times x plus 2. And you can kind of see real quick how that would factor. You would say, I need to multiply to get a 3x squared, so that's going to be 3x times x. And then in the end, you need to multiply to get a 2. And the only way to get 7x in the middle is if you put plus 1 with the 3x and a plus 2 with the x. And you can FOIL that out or multiply to make sure that it is what you started with. And then set each factor to 0, and then solve for x, and you'll get that x is negative 1/3 and negative 2. And so if you go back to your list of possible rational zeros, both of those numbers were on the negative side of the list. So we could have tried more numbers, but this one was just quadratic, so we could just use our factoring techniques. So the zeros of our function are negative 2, negative 1/3, and 1. Meaning, when we plug in each of those numbers back into the original, you're going to get 0. So that's what it means to be a real zero. And then what that also tells us is how to write our function factored. And so the same polynomial that we started with here, once we find the real zeros, once we find these real zeros of the function, we can factor it, and it looks like x minus 1 times 3x plus 1 times x plus 2. And so just some things to mention. Once you know the factored form of the polynomial, it actually makes it way faster to graph it, because you know your x-intercepts. And if you didn't already know your zeros, which we figured them out to get to the factors, you could see the zeros right away. It's the numbers that you plug right into these x's to make each of these factors 0. Okay, let's go ahead and do another one. So we're going to find the real zeros of this 4th degree polynomial and write it in factored form. So this one has at most 4 real zeros because the degree is 4. Then from Descartes' rule of signs, notice that this goes positive to negative, so that's one sign change. Negative, so there's none there. Positive from negative, that's a second sign change. And then positive again, so no sign change there. So we have 2, or subtract 2, so 2 or 0. So 2 or 0, positive real zeros. And then if you plug in a negative x into your function and simplify, so put a negative x everywhere there's an x, and simplify, you're going to get this version of your polynomial. And then if we count the sign changes, there's none here, there's 1 here, none there, and 1 here. So 2 sign changes, so 2 or 0, negative real zeros. Okay, so that's Descartes' rule of signs. And now your list of possible rational zeros, take the factors of the constant, which is 2. So factors of 2, and divide them by the factors of the leading coefficient, which is also happens to be 2. So divided by the factors of 2. So that would be positive and negative 1 on top, positive and negative 2 on bottom. And then you break those apart, remember? So you say 1 over 1, you say 1 over 2, and then 2 over 1, and 2 over 2, which is already on the list. So if you expand this list, this is negative 2, negative 1, negative a half, 1 half, let's put it in order, 1 and 2. So this list has 6 numbers on it, and at most we know there's 4 at most possible real zeros. We also know from Descartes' rule of signs that there's either 2 negative or no negative real zeros, 2 positive or no positive real zeros. Okay, so let's go ahead and use synthetic division again. So make a choice, and we keep picking 1 here just because 1 is really easy to work with. You don't always have to choose 1. Just be aware you can pick any number you want. We're just picking 1 because it's easy to work with. So bringing down the 2 and starting to multiply. 1 times 2 is 2. Add that and get 1 here. And then 1 times 1 is 1. Add that, get negative 4. 1 times negative 4 is negative 4. Add this, get negative 2. 1 times negative 2, and add this and get 0. So this is going to be a factor and a real zero because the remainder was 0. That's what we want. We want this spot in our division to be 0. Okay? And so x minus 1 happens to be a factor, just like on the previous example. But we could have picked something else from the list. Just be aware that 1 is usually nice to work with. That's the only reason we picked it again. Okay, so remember what we're going to do next, just like we did on the last one. We're going to take this third row of our synthetic division, and we're going to use this to simplify our polynomial function. So if this came from x to the 4th, then when we divided using synthetic division, this is now 2x to the 3rd plus x squared minus 4x minus 2. And so our function has our factor x minus 1 times what's remaining after our synthetic division. Okay, so we're going to complete the repeat the process, because this one that's left over, this factor, this depressed equation, it's not a nice quadratic one like last time, so it's not too easy to factor like we did before. So we are going to use our list again. Okay, so on the list, if we write it out, we had negative 2, negative 1, negative 1 half, 1 half, 1, and 2. And remember what Descartes' rule of signs said. It said if we had we had 2 positive real zeros or none. Since we found one of them, that means that there's got to be another one, because it was 2 or none, 2 or 0 positive real zeros. And if we found 1, then there has to be 2, because the list didn't say 1, it said 2 or 0. And so we found 1. That means there's another positive number, and they can repeat. And so you can pick 1 again, or you can pick 1 half, or you can pick 2. So it can repeat, so we could pick any of them again. So we're going to go ahead and pick 1 again to test it. And if you test 1 this time, and you're testing it into the depressed equation, so notice the coefficients in your synthetic division. Let's just highlight that. That's 2 from the x cubed, 1 from x squared, negative 4 from negative 4x, and negative 2 from here. If you do your synthetic division, it's not going to equal 0 this time, so this one is not a repeated 0. Okay, so we tested it, and it's no longer going to work, so we want to check another number. Okay, so it's not going to be one of our factors, so let's try 2. So from our list, we'll try the number 2. So using synthetic division, Same thing, we'll work out the process, and we want this to be 0, and it's not. So that one is not a real 0. Okay? So we'll try a negative number this time. Let's see what happens when we pick the negative 1/2. Okay, so negative 1/2. I'll work this one out with you because it's fractions. So bring down the 2. Negative 1/2 times 2 is going to be negative 1. And when you add that, you're going to get 0. Negative 1/2 times 0 is just 0. Add that, you're going to get negative 4. And then negative 1/2 times negative 4, that's going to be positive, and 4 divided by 2 is 2. And when you add that, you get 0. So this is good. So we found another 0 from our list. So negative 1/2 is a 0, meaning that the factor, remember the factors are always x minus that real 0. So x minus negative 1/2 turns into x plus 1/2. So far we have x plus 1 was a factor. No, I'm sorry, x minus 1 was a factor. And now we also know that x plus 1/2 is a factor. So we found 2 factors. And so then we focus on this last row here to simplify what we have remaining. So let me remind you how this worked. This was now from the depressed equation of x cubed. And so this third row is now going to be 2x squared plus 0x minus 4. So our polynomial, our 4th degree polynomial, looks like a factor to x minus 1 times x plus 1/2 times what was left over from finding this second real 0. So 2x squared minus 4. And from here, we can go ahead and just solve that one. Other versions of it, not using our list anymore, because once you're at a quadratic equation, once this is quadratic, use something else. Use factoring, use your quadratic formula. You don't have to refer to your list any longer. Okay, so if we factor this one, we're going to get x equals plus and minus square root 2. Okay, so what happened was our list only gave us possible rational real zeros. So let me write that list down again. This was our list. And using this along with Descartes' rule of signs, let me kind of summarize what happened. Descartes' rule of signs said that we had positive real zeros, 2 or 0 of them, and negative real zeros, 2 or 0 of them. From our list, we know that 1 was one of the positive numbers, and then we tried 2, it didn't work. And then we tried negative 1/2, that also worked. So we know that we had to have 2 positive and 2 negative real zeros at this point, because we had 1 of each so far. And then what we ended up doing at this last part was we're finding out that the last 2 real zeros were not rational zeros. That's why they weren't on our list, and that's why when we tried some other numbers, they didn't work. Because these last 2 real zeros, positive square root 2 and negative square root 2, notice that we have another positive one, so the second positive number, and another negative number, the second negative number. So these were both true, but they're not rational numbers. These do not fit the form of a rational number. So they're, even though they're real zeros of our function, they weren't on the list. But that's okay. You just try numbers from the list until you get to a quadratic equation that you can work out. And so the real zeros of our function are in order: negative square root 2, negative 1/2, 1, and square root 2. And so to factor that, we have just the following. We can factor the last factor that we had, the 2x squared minus 4. Just go ahead and factor out the 2. Even though we can write this with our square roots, we can say x minus square root 2 and x plus square root 2. Normally we don't write our factors like that because those are not nice numbers, those are irrational numbers. So we would leave it like this. We would leave it in this factored form. Okay, so we have our 4 real zeros, but we only see 3 factors with x in them because we don't want to write it like this with these irrational numbers. All right, one last example. We're going to actually find the real solutions to this equation. So before we were finding just the function, the f of x we're finding the real zeros, but now it says solve this equation, and so the answer is the real zeros. So we already did all the work, but I want to just point out the difference to you. So previously we were given a function and we were told to find the real zeros and factor it, and now we're taking a function that equals 0. So this is the new part, that the function starts off with an equal sign equal to 0. This is exactly the same thing as finding the real zeros when you're asked to solve an equation that equals 0. So we already did all that work, and so the solutions to this equation this time are the 4 real zeros that we found. Okay, so that's it for this one. And we put together all the things we learned so far to be able to find the real zeros of our polynomial functions and factor them. So to kind of sum that up from what we know that if we find a real zero, that number c makes the factor of one of the factors of our function. So we can find all the real zeros, and then we can write out our function in factored form, and so on. And then the numbers that we found, those are called the real zeros of our function, and that's because when we plug them in, you get 0 out of your function. Okay, so that's what we've been working on. And so the last thing to mention for this one is these last 2 theorems. And so we have 2 here that says, the first one says every polynomial function with real coefficients can be uniquely factored as a product just means we're multiplying, of linear factors or irreducible quadratic factors. So that just means that you could take your polynomial function and you can factor it like I had written just a moment ago. These are all linear factors here. Linear meaning that the degree on x is an invisible 1. Or if you can't break that down without having your irrational numbers, you could have a quadratic factor. So something like we had here. We'll call that one. So that's what irreducible quadratic looks like this one here. And then the other theorem says that a polynomial function with real coefficients, if it has an odd degree, then it has at least 1 real zero. So that's just an interesting fact. Okay, so that is it for this one. Thank you for watching.